Hello, everyone. Paul here in the lower right hand corner. Hello. And today we're going to talk a little bit about the scientific method. Now, I can pretty much hear you guys rolling your eyes from here. And I'm just recording this, but I can still feel you all rolling your eyes because, every single time you've taken a science class, right? Some science teacher or a science professor of some kind or another has said, okay, we're going to talk about the scientific method. And, first you have a hypothesis, and then, I don't know, that gets magically turned into a theory. And then, once you prove your theory, then it becomes a law, and, you get that, right? Yeah, none of that is true. Okay, nothing that I just said is true. It's just not. And so, what we want to do today is we want to get into a little bit more about what the scientific method actually is. Now, there is a little bit of wiggle room here because, when we talk about the scientific method, what we're really talking about. Some water there. What we're really talking about is describing, how it is that scientists think. And that's not always an easy thing to do. Because well, think about it, right? Think about it. But if I ask you a fairly complicated question, and then I said, okay, I'm going to leave the room for I don't know, 10 minutes, and I'm going to come back, and we're going to talk about this question. If I did that, sorry, my phone's going off here. If I did that. So I leave the room, I come back, and let's say that I come back and I say, okay, I don't really care about the answer to the question. I want you to write 250 words about how you thought about it. Tell me how you thought. Well, I don't know. I don't know. I would be hard pressed to describe how I think. I don't know. You just think. I don't, how do you describe that? But yeah, with the scientific method, that's what we're having to do, right? We're having, science is not a topic. Science is a way of thinking, right? It's a way of approaching the world. And so, now, there's going to be some things that we all kind of have in common, but it's going to be kind of different around the edges, if you will, just because different people have a little bit different approach. But there are some things that we're all going to have in common, and that's kind of what I'm going to talk about today. And so, just by way of introduction, I put up some pictures here of some famous geologists. Some of them we'll be talking about, some of them we won't, but one of the ones we will be talking about is this guy in the lower right here. This is Harry Hess, who was one of the great geologists who kind of founded the idea of plate tectonics, and we'll be talking quite a bit about him. Here is Charles Lyell. That's a young Charles Lyell, pretty much the founder of the modern science of geology. He wrote a book in the 1800s. He lived in England, called Principles of Geology, oddly enough. And that was kind of the book and the technique that got the entire science rolling. And we'll talk a bit about him. One of his admirers, students, and later colleagues was this guy here, up the upper left, who you might recognize. That's Charles Darwin. That's old Charles Darwin. Charles Darwin was mostly a geologist. I know that he's very famous for evolution, which is kind of biology, but he really was a what we would call a natural historian. He did a lot of things, and he did a lot of geology. He did an awful lot of geology. We geologists are awfully proud of Charles Darwin. He did a lot of really outstanding work. The guy with the gun here, kind of in the middle, is Roy Chapman Andrews. He's in the Gobi Desert, and he's got a gun because if you didn't, the locals would kill you and steal the fossils that you had found. And so he literally had to fight them off. Now, that the fossils might have belonged to the locals to start with is a whole other conversation about science and imperialism that we could have, but we'll give that one a skip for now. The guy in the spacesuit standing on the moon is the only guy in this picture who is still alive. That's Harrison Schmitt. Harrison Schmitt is the only scientist to walk on the moon. All the other guys who walked on the moon were test pilots because they were mostly concerned with, getting there and getting back. But by the time Apollo 17, the last Apollo mission, rolled around, they were like, hey, let's send a geologist to that great big rock that orbits the Earth, and they did. I mean, it was more than that. But anyway, and he was able to actually do a lot of really good work. You go to an area, you don't want to just pick up any rock. You want to pick up the one that's going to tell you something. And, he had been working for a long time training the astronauts to kind of be geologists. But, he is an incredibly talented geologist and was able to do a lot of really good work. So anyway, yeah, so that's my slide. And a friend of mine, a woman, was looking at this slide one time, who's a geologist, and she said, Paul, what's that? And I said, well, that's just my scientific method intro slide. It's not a big deal. And she said, Paul, why are all your geologists men? And I'm like, dang, they are. And they're all white men, and with the exception of Harrison Schmitt, they're all dead. And so here, new slide. Much better slide, right? This is the fun thing now. Now, not all these people are geologists, but they are all scientists, and a couple of them are geologists. Actually, Mary Anning over here in the painting was a great paleontologist. A lot of the fossils that you would probably recognize were discovered by Mary Anning. She actually supported herself and her family, I believe, after her husband died, collecting and selling fossils. Made a great living and did a lot of really very good work in the field of paleontology. Let's do the other geologist. And that's Tanya Harrison down here, lower right, in front of the mock-up of the Mars rover. Tanya Harrison is the chief geologist for the Mars rover program. So the current rover Curiosity on the surface, and then the 2020 rover, whose name escapes me, that is on its way to Mars now. She helped design the geology instruments. She's in charge. She analyzes the data when they come back. She's got all that going on. She does some really interesting geology on Mars. Speaking of space, the woman floating in the International Space Station right here in the middle is Mae Jemison. She is I think she's a chemical engineer or something like that. First African American woman to fly in space. And just all-around amazing person. She did a cameo on Star Trek Next Generation, by the way. There she is, standing there with Nichelle Nichols. And so, and she's doing a really interesting project right now where she's studying the effects of very long-duration space flight. If we're going to go anywhere outside of our solar system, it's going to be generations of people to get there. I mean, there are going to be people who are born and live and die in space. There just are. Warp drive is unfortunately not actually a thing. And so, what does that do to a person, right? What kind of biological changes, sociological changes, good grief, the list just goes on and on and on and on. And she is working on that, which is just remarkable. And then upper right with the gorillas is Diane Fossey. She studied African Highland gorillas and was killed by gorilla poachers. There's a really good movie about her called Gorillas in the Mist. Sigourney Weaver, I believe, plays Diane Fossey. And so she was one of three women who Richard Leakey, a very famous anthropologist, hired to study primates. Women, y'all are just better at studying primates than men are. I don't know why, but y'all are. And Richard Leakey understood this, and he hired Diane Fossey to study African lowland gorillas. Another name, upland gorillas, I'm sorry. Another name that you may have heard, Jane Goodall. Studying chimpanzees. And then another name you probably haven't heard, Barunti Galdinkas in Indonesia right now, studying orangutans. And so, which is important work, right? Orangutans are disappearing at a prodigious rate. And so understanding them and their environment and their habitat is vital right now because they really are just disappearing. So the good thing is if you want to be a geologist or a scientist, you can be a geologist or a scientist. I'm not pretending there aren't still barriers, because there are. Let's not make too happy about this, but they're at least not institutional, right? It's at least not like the rule that no girls can major in this, and so that is progress, if nothing else, and so yeah, so you can get where you want to get to from where you are, and that is always just a good thing. So okay, so let's get a definition of science, because before we launch into how we do science, it might be good to know what science is. And the woman you're looking at is Zelma Jackson. Zelma Jackson is a resource geologist. Zelma Jackson finds uranium in Montana. Okay, so you think about this, and I'll say this at some point, probably on my first lecture. Look around you. Everything you see has some sort of basis in geology, right? If it wasn't grown, it was mined, and if it was grown in soil. That's geology. We're going to do a whole thing on that. If it's plastic, that's petroleum. Some geologist somewhere had to find it at some point. If it's metal, that had to be extracted from an ore that had to be found somewhere. And so, yeah, geology comes into places you really might not think it does. And if you want to build a nuclear power plant, you're going to need uranium, and Zelma Jackson will find it for you. So it's a really extraordinary thing. So what is science, though? Well, science is a way of investigating. Now, I say the universe here. I don't mean like astronomy, right? I mean just about anything. Now, it's not the only way of understanding things, but it is a good way, as we'll see here in a few minutes. In order to be science, there are three things that your idea or that your investigation needs to have. First of all, your idea needs to be testable. And honestly, this is really the hallmark of what science is, right? It is testable. If your idea isn't testable, how will you know if you're wrong, right? I mean, you could be thinking, something that sounds perfectly reasonable. And believe me, people have. I mean, there's all kinds of things out there that sound really good, and people assume they're true, and then you go and you actually test them, and suddenly you realize that, oh wait, no, that's not true, right? And so, I mean, a really good example has to do with falling objects, right? If I have two things, if I have, let's say a wooden ball and an iron ball, and I don't know what the densities are, but let's just assume that the iron ball weighs twice as much as the wooden ball does, and I hold them up and I drop them. Okay, which one's going to fall faster? Well, the iron ball falls faster. Okay, great. How much faster? Well, it weighs twice as much, so it should fall twice as fast. That just sort of seems to make sense. So it'll fall twice as fast, so it'll hit the ground in half the time. Weighs twice as much, falls twice as fast. Totally reasonable, except it is utterly and completely not true. And so I'm gonna link. It just occurred to me. I usually show this video at this point, but YouTube is kind of funny about that. I'm gonna link a video of people dropping a bowling ball and some feathers in a vacuum chamber. Okay, and just watch it because it's a lot of fun. But because here's what happens: they hit at the same time. Right? And, Galileo figured this out. Galileo, legend has it, and I prefer to think it's true because it's really cool, went climbing up into the Leaning Tower of Pisa and started throwing things off of the Leaning Tower of Pisa of different weights and timing how long it took them to hit the ground. And he realized that, that heavier things fell faster, but not that much faster. Not that much faster at all. And he kind of figured that the difference was the air. That if he could take away the air, everything would fall at the same speed. And it turns out he was right. The problem is, back when he was alive, there was no way to take out all the air. Now there is. Okay, and I'm going to link a YouTube video showing you what happens when you drop things in a vacuum. It's really, really kind of remarkable. But what I'm getting at here in that very roundabout way is testable, right? You can think a lot of things that are utterly untrue. if you don't test them. So we need to be able to test our ideas. The other thing is scientific ideas are natural as opposed to supernatural. Okay, we don't do God. One way or another. I'm not saying that all scientists are atheists. We're not. I'm not. Okay, but science has nothing to say about God one way or another, or any other deity. Okay, so your scientific ideas need to be based in the natural and not the supernatural, and then also observation based. And this kind of gets back to testable, right? Don't just sit around. If you're thinking about, I don't know, frogs or whatever, okay, don't just sit around and think about how you think frogs should be, or what's the sort of, I don't know, the Greeks did a lot of this, right? The platonic ideal of a frog. No, 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 no. If you want to know about frogs, go out and look at some frogs, right? Geology had a very bad habit for a long time of doing this. For a long time, the science of geology, in particular in England, was run by old white dudes sitting in overstuffed leather chairs, sipping brandy, smoking cigars, and talking about rocks. Okay, it would take a geologist named Will Smith, yes, Will Smith, to actually get out there and get his hands dirty in the rocks and actually kind of found the field portion of geology, and we'll talk more about Will Smith. But yeah, don't just get out there and do it, right? Make some observations, and and this comes back to testable, right? That's how you test your idea, is by making observations, right? Natural also comes back to testable. There's really no way to test for the existence of God. That really doesn't work. Doesn't mean you're wrong, just means you're not doing science. So if what you're doing is testable, natural, and observation based, odds are it's science. I mean that's a pretty good metric. So how do we do it, right? How do we do science? Well, this was my old slide on the scientific method, and if you're taking notes, for God's sake, don't write this down. It's a hot mess, and I honestly, I built it a little bit at a time, but it's still a hot mess. And my idea was, well, it's a hot mess because it's a hot mess, and that's just the way it is, and you just need to deal with it. But turns out it's really not a hot mess. It's a lot simpler than this, or at least it can be. And I was watching YouTube videos one night, and you know how you watch one YouTube video, and then they queue up another one for you, and that's kind of like the one you're watching, and what's that one too? But next thing you know, it's 3 a.m. and yeah. So I was doing that, and up comes this guy, Richard Feynman. Richard Feynman is a giant of 20th century physics. He's one of the founders of the whole quantum mechanical revolution. He was a great physicist. He won at least one and maybe 2 Nobel Prizes. I think maybe one. I don't remember. Anyway, great scientist. Amazing science. Absolute pig in his personal life, by the way. We will admire Richard Feynman for his science, but nothing else. Okay, he was not a good guy. But anyway, his science was amazing. And he was delivering a lecture to a bunch of undergrads somewhere at one of the UCs or something, and he laid out the scientific method in a way that I was just like, oh, that's much better than mine. And of course it is. It's Richard Feynman. And so you saw my slide on it. Here's Richard Feynman's, and it's much better. It really is much better, right? So here's what to do, right? You see something going on, make a guess, right? And this sounds weird, and I'm gonna make it different and maybe a little bit more comprehensible here in a second, right? Make a guess. And then, like Richard Feynman said, determine the consequences of your guess, right? And so ask yourself, if I am right, then what? Right? And then compare your consequences to nature. In other words, go look for the what, right? And so here, I rewrote it in a little bit better way, right? So you look at something and you say, if I'm right, then what? And go look for the what. Okay, so let me give you an example. So let's say that You come out in the morning, you put your keys in your ignition, and you turn the ignition, and your car doesn't start. Okay, so what are we going to do? Well, this is something that a point that I'll make more explicitly later here in a few minutes. But when people have an actual problem to solve that they really need a solution for, they usually do science, or they get someone to do science for them. If your car's not starting, you don't go find a goat to sacrifice to the car god in the hopes that your car will start. No, right? You need to troubleshoot it, figure out what the problem is, or you need to hire someone to, or something. So let's say it's not starting. Okay, well, what do you do? Well, okay, so make a guess. I think my battery's dead. Awesome. Okay, you think your battery's dead. That's reasonable. What are the consequences of your guess, right? So what you do is you say to yourself, okay, if my battery is dead, then what? All right, okay, so if my battery's dead, right, and now I'm kind of down on my little paraphrase, right? If I'm right, then what? Look for what, right? So if my battery's dead, then my electric window shouldn't go down, right? So look for that, right? In this case, flip the switch. Do your windows go down? Maybe not. Maybe let's say they don't. Or if they do, they go down very slowly, right? So, what do we do now? Right? Well, you do it again, right? Because more is better, right? So say again, right? If my battery's dead, then what? Then my windshield wipers shouldn't work. Great, flip the switch. Do they work? No. Okay. If my battery is dead, see, and I'm doing this over and over again, right? This is what scientists do, right? We have an idea. My battery's dead. What do? I test it, right? I test it by asking myself, what should I see? And then I go look for that, right? So let's do one with geology. Let's do one with extinction. I'm a paleontologist, so let's play around with mass extinction, right? And let's ask ourselves, okay, why did the dinosaurs go extinct, right? What caused that extinction? So then you say to yourself, okay, I think an asteroid caused it, right? I think that an asteroid hit the Earth and one way or another caused that extinction. Great. Okay, so now, right? There's our guess. An asteroid caused the extinction of the dinosaurs, or let's say the non-avian dinosaurs, because all birds are dinosaurs. Okay, so that asteroid caused the terminal Cretaceous extinction, which reminds me I need to get you guys that time scale that I said I would last time in the intro. Anyway, so an asteroid. Okay, so then you say, okay, well, if an asteroid caused that extinction, then what, right? What should I see out there? Well, everything should go extinct at like the same time. Right? Dinosaurs, non-avian dinosaurs, should be doing fine. They should be cooking along, right? Because look, it's not like they're going to know this is coming and commit suicide or something. They're not, right? They're just going to be going along, cooking along fine. And then all of a sudden, bam, in like a day, right? Everything that went extinct should go extinct in a very short period of time, right? So that's, the pattern you would expect. So what do? We go look for it. Right? We go look for it. We see if we see it. Turns out it gets complicated. Turns out it gets very complicated, but that's the way that works. Okay? So, right, you say you have an idea. You say, look, if my idea is right, then, what should I see? Go look for that. That's how we do science. Notice that I haven't talked about any hypotheses or theories or laws or any of that weirdness, right? We just have ideas, okay? And we test them. Right, we test them by asking ourselves, if I'm right, what should I see? And go see if you see it. Okay. Now here's the fun part. You can never prove that you're right. You can prove that you're wrong, but you can never prove that you're right. Right. If I think my battery's dead, and I flip my windows switch and the windows roll down, and I turn my windshield wipers on and they go just fine, and everything seems just fine, everything electrical seems to be working okay, my battery's not dead. Okay? I mean, it might be kind of dead, but let's just take the simplistic case. Not dead. Okay? Okay, but now let's do it this way. Let's say that you flick your electric windows; they don't work. Your windshield wipers don't work. Your radio's not coming on. Nothing electrical is working. Battery's probably dead. So pull the battery, right? Take it down to the battery store, right? They sell you a new battery. Awesome. You come back. You put the new battery in the car. You drive away, and everything's good. Awesome. At any point in that process, did you prove that your battery was dead? Not really, right? Because there are always going to be alternatives. It could always be something else. Maybe you've thought of something else and you've allowed for it, but maybe you haven't. And in an infinite universe, you can never think of everything. Maybe the battery wasn't dead. Maybe the terminal wire was loose, right? And you didn't realize that when you pulled the battery. Okay, and so you pull the battery, you take it to the battery store. Their job is to sell batteries. They don't make money not selling batteries, so they're happy to sell you a new battery, right? And you take it back, you put it in your car, you tighten everything down. There was the problem. There was the actual problem, right? But you tighten everything down, you drive away, right? You happily thinking that you solved the problem when all you really needed to do was notice that loose terminal connector, right? So no, your battery wasn't dead. Okay, let's make it a little harder. Let's say that you take it to the battery shop and they put it on a tester, right? And they say, oh yeah, it's dead. Look, you need, I don't know how this works, right? You need 12 starting amps and you have 3 or whatever. And it's not holding a charge. Yep, you need a new battery. Awesome, okay. They sell you a battery, you put it in your car. Still, in the process of putting that tester on the battery, did that prove the battery? No, that didn't prove the battery was dead, right? Maybe the machine's messed up, right? Possible. Now, once again, we're getting a little less likely here, okay? But maybe the machine's messed up. Maybe, once again, that battery store, they don't make money not selling batteries. So maybe everyone has a dead battery when they go into the battery store, because the machine is rigged, right? That's probably a little more likely, but anyway, no. So once again, though, we didn't prove anything. Okay, let's make it a little harder. Let's say that your dad owns the battery store and you're broke. So he's just going to need to give you a battery. Okay, and so you go to your dad's battery store. You say, Dad, my battery's dead. He says, well, let's check it. And he puts it on his battery tester. And sure enough, the battery's dead. Maybe he even puts it on a second battery tester just to make sure. But it's dead too. So your dad says, fine, I know you're broke. Here's a battery. Go put it in your car. So great. Okay. So you put it in your car. You drive off. Okay. So now what's our alternative now? Right? I mean, the loose cable's not going to work because right. So now I don't know. Our dad needs to be in some sort of a conspiracy with big battery you see, and now right, once we start talking about conspiracies and things like that, once we talk about all the scientists faking the climate data or something weird like that, now we just went off the deep end. Right now, despite not proving it, it's still true. Right? And I don't want you to confuse these two things. Just because we haven't logically proven something doesn't mean that it's not true. Right? There are things that have piles and piles of evidence supporting them, all kinds of ideas, right? Look, we haven't proven a single idea in science. And yet, I don't think anyone's going to go jumping off the roof because they don't think gravity is real or something like that, right? And so don't confuse this sort of logical sense of proving things with, them being true, right? There's a lot of things that are certainly true just because, once again, the alternatives are stupid, right? And there comes a point where when someone says, well, no, the battery's not dead. There's this conspiracy between your father and the government and big battery and QAnon and weird, I don't even know, right? No. The battery's dead. Okay, so yeah, so in a weird, so you can never prove your theory, and there's that word. A theory is just an idea about why something is, right? So you can never prove your theory, but you can disprove it. Right, so once again, you can never prove you're right, but you can prove you're wrong. Right, if you think your battery's dead and you take it to the store and they put a tester on it and go, no, it's fine. Okay, you were wrong. Go maybe I don't know what is it now, your fuel pump, your starter, I don't even know. Okay, this is why I have mechanics. But anyway, so but this is weird now, right? Because look, right, because we all kind of grew up, myself included, learning that, well, if I have a theory and I prove it, then it becomes a law, right? I just told you can't prove anything, right? Because there's always an alternative that could be true. Okay, so you can't prove anything. So then, what's the difference between a theory and a law, or maybe where do laws come from if they're not just theories that we can prove, right? Well, let's think about this. And I've got a drawing pad here, so I'm going to write. So bear with me just a little bit. But if I think about laws, the first law that most people think of is, the law of gravity, right? Which says, if I take the force of gravity, get rid of that. There we go. Force of gravity equals the mass of the first object times the mass of the second object divided by the distance between them squared, right? Or Isaac Newton's laws of motion. Sorry. Need a G there, and then you multiply by a constant, big G here, just to make the numbers look pretty. Isaac Newton's laws of motion are all derived from this formula: force equals mass times acceleration, right? The ideal gas law, the pressure of a gas times its volume, equals how much of it you have times the constant times the temperature, also known as Pertnert. Kepler's third law of planetary motion, the period of a planet squared equals its distance from the sun cubed, right? These are laws, right? But notice that they're very specific, right? Gravity, I've got three things, right? Or three terms. I've got the mass of the first object, I've got the mass of the second object, and the distance between them. That's it. Okay, what this formula does is it lets me calculate the force between two objects, right? Isaac Newton, force, mass, acceleration, right? The pressure of a gas, its volume, how much of it do you have? A constant, just to make the numbers look pretty, and the temperature, right? This describes a gas in a closed container. Right, if the temperature goes up, the pressure goes up. If the amount of the gas you have goes up, et cetera, right? And so, this does not describe a gas like our atmosphere, right? This just describes a gas in a closed container, right? The period of a planet, how long it takes it to go around the sun squared, equals its distance from the sun cubed. Very powerful stuff, but also fairly simple. And that's the way laws are. I'm going to erase these while I talk. That's the way laws are, right? Laws are pretty simple, really, and they work under very precise and very restricted conditions, right? They're very powerful. They can tell us a lot of things about the world around us, but laws usually aren't the big ideas that we might think they are, right? A law is an explanation that works under very specific and very narrow conditions, right? Force, mass, acceleration, right? The mass of two objects, the distance between them, right? That's what a law is, okay? Theories are much bigger things, right? A theory is a much bigger idea, right? If we think about theories, we think about maybe the first one we think of is, the theory of relativity, right? Which, we can write E equals mc squared, but that's only a very, very small part of that, right? Relativity, is all about how, space and time and gravity are all related in ways that, that are really kind of weird, and just all kinds of very, very strange stuff. We'll talk about the theory of plate tectonics, right? The idea that the surface of the earth is moving. And that movement is what causes volcanoes and earthquakes. It's not a theory because we're not sure. It's a theory because it's a huge idea and one that we're never going to have locked down. I'll never be able to write a formula or something weird like that for plate tectonics, right? It doesn't really work that way, right? Evolution is the same way. It's a big idea about how organisms change through time in response to environments changing and genetics and all kinds of crazy stuff. And it's never going to be a simple thing that I can just write in a sentence or two or something like that, right? It does not work that way. It's a big idea. It's not a theory because we're not sure. It's a theory because we'll never really know everything about it. Same with plate tectonics. Same with all kinds of things. Right? Just choose your favorite theory, okay? And that's the way that works. But honestly, really and truly, I don't even want you to worry about that. Because really, I don't even like using the words theory and law, and because it implies things that simply aren't true. Right? When you say the word law, people think that, well, it must be true. Or you say the word theory and people think, well, maybe not. It really doesn't work that way. And I'll talk more about that here in just a second, but it really doesn't. And honestly, it's really haphazard, and I don't want you to get hung up on is an idea a theory or a law. It really doesn't matter. Okay, it's not like all the scientists sit down once a year and vote on whether or not something should be a theory or a law. What we call an idea is really kind of random. I'll get here. Let me give you some. Let me show you the random. So people like to say this. Well, evolution is just a theory, never been proven, right? Well, hopefully we're over the idea of ever proving anything, right? Because we don't. Okay, so if you're waiting around for people to prove a theory, don't, because it's not going to happen. Okay, and scientists are ourselves guilty of this sometimes. You'll hear someone say on the news, "Well, I just proved my." No, you didn't prove anything. Don't even say that. That's just not true. Okay, so and once again, it's really kind of random. Here, let me show you some examples. So gravity is both a theory and a law. That formula I wrote before is the theory part. But if you want to hear a physicist stutter sometime, ask them why there is gravity, right? In a universe with two things, I don't care how far apart they are, they're going to hit. They could be a bazillion trillion miles away, but if that universe only has two objects in it, I don't care how small they are, they're going to hit. Okay? Because they're attracted to each other. Objects are attracted to each other with a force that is proportional to the product of their masses and inversely proportional to the distance between them squared. They are attracted to each other, and we have no clue why. We know they are, we do not know why. Isaac Newton's laws of motion don't work when the things moving are either very small or moving very fast, like subatomic particles. Isaac Newton's laws of motion do not work for subatomic particles, which is everything, right? Electrons, protons, neutrons, quarks, whatever. They don't work. They simply do not work. Now you need, if it's just moving fast, you need Einstein and relativity to explain the motion. If it's very small and moving fast, now you need Richard Feynman and all those quantum mechanics guys to sort it out. And then it really stops making sense. That quantum mechanics, that's just witchcraft. This is weird. But anyway, paleontology, I love this class. I get to talk at least a little bit about paleontology. In paleontology, we have something called Cope's rule. Great. It's a rule. Right when you think you got the whole law theory, then along comes a rule, right? We'll also talk about like the principle of cross-cutting relationships, right? Don't assign importance to what we call an idea. Okay, if it's a rule, a theory, a law, a principle, a hypothesis, it really doesn't matter. That is very, very random. It's not systematic. And so if you take nothing else away from my scientific method lecture, I want you to maybe understand that scientific ideas need to be tested, that and what we call an idea doesn't mean anything, right? That's kind of the short version, right? And then just for fun, another paleontologist, Lee Van Valen. By the way, Cope's rule is just the idea that as things evolve, they tend to get bigger. Some things do. We did. Other things don't. Trilobites didn't. So I don't know. It's a rule. It's like a trend. I don't know what it is. It's an idea. Eh, sometimes it works. It's interesting. Lee Van Valen, a very famous paleontologist, did some really interesting work. Published a paper called "The Red Queen Hypothesis: A New Evolutionary Law." So in one sentence, he calls an idea a hypothesis and a law and puts it inside of the theory of evolution, right? And so if you're trying to work out the importance of this idea or whether or not the idea is true based on what we call it, your head is going to explode. Okay, don't do that. The Red Queen Hypothesis, by the way, is just the idea that you never stop evolving, right? It's not like you get somewhere and you go, "Whoo, I'm here, I can stop now." No, you can't. No, you can't. Okay, there's not a place that you get when you're evolving that you're done now. Okay, because everything around you is still evolving. You have to run in place just to keep up. Hence the Red Queen from Alice in Wonderland, right? And so once again, don't assign importance to what we call ideas. We have an idea. We test them. If they work, we use them. If we don't work, we get rid of them. That's just kind of the way that is. So I also, though, want you to get to the idea that the scientific method is not limited to, quote unquote scientists, right? Lots of people use it. Look, if you take if your car doesn't start and you don't want to troubleshoot it, you see yourself, you take it to a mechanic who, guess what, is going to be doing science. Right? They're not going to go out back and sacrifice a chicken to the alternator god or something like that, right? They're going to troubleshoot your problem with science, okay? They're not just going to randomly replace car parts until your car runs, although maybe sometimes it seems that way, but they're not. Right, and so engineers, right? An engineer is basically a scientist who builds things, and I really need to update my smartphone picture. But anyway, scientists are engineers who build things, and if you want to know whether your idea is working or not, build something with it right away. You're going to find out, right? If we think the ideal gas law is true. Right. If we think that, let me write it down again. Right. If we, I'm sorry, I'm just really enjoying my marker here. Bear with me, guys. And so, if we think that this is true, that the pressure of a gas times the volume equals how much of it you have, times a constant times the temperature. Right. Well, if we say to ourselves, okay, look, an engineer, a scientist looked at this and goes, okay, that's cool. Right. An engineer looks at this and goes, hey. If I take that temperature and jack that temperature up, that means that this pressure, I can't circle things, is also going to go up, right? And so, if I build a box, let's say, and I'm trying to draw with this is going to be really interesting, but that's not too bad. Okay. So anyway, if I build a box, right? Sorry, terrible drawing, but anyway, I build a box and I fill it with gas, right? And then, I mix that gas, and let's say when those gases are mixed, they burn. Suddenly my temperature has shot up, my pressure has shot up, so now that gas is going to go out this side. Newton tells me for every action there's an equal and opposite reaction, so if the gas shoots out that side, that shoots that way, and we just built a rocket engine. Right? That's what engineers do, right? They take scientific ideas and they build things out of them, right? And so, and so the quickest, I'm trying to find my eraser. Hold on one second here. There it is. Okay, so one of the quickest ways to know whether or not your idea works is to build something out of it, right? And so like I said, engineers are just scientists who build things, right? Also, though, something that is near and dear to our heart right now, especially recording this in the midst of the COVID outbreak, is medical research. Right? We're just not going to start injecting people with random stuff until we find something that we think might kind of work. No, that's not the way medical research works, right? If I've got 1,000 people that have something, I don't inject them all. I inject half of them. In fact, I don't even inject half of them. I get someone else to inject half of them, and they don't know if they're getting the medicine or a placebo or not the medicine. And then, we see if the people who actually got the medicine got faster at a higher rate than the people who didn't get the medicine, right? That's the essence of medical research, right? We have an idea. We think that this thing will cure whatever. Great. How do we test that idea? Well, I'm going to get a bunch of people who have this, and I'm going to give it to them, and we're going to see if they get better, but we're not going to give it to everyone, right? You just give it to half the people, which brings up an interesting, let's do medical ethics for just a second here. Because something like COVID, you might be it's kind of easy because it's not. I mean, it's not good at all, but it's not terribly fatal. Not like Ebola, right? Let's say rather than COVID, let's say that that you got a bunch of people who have Ebola, right? Are you really only going to give the medicine to half of them? Ooh, I don't know. Really? That seems kind of hinky now. And we didn't. Ebola. If you had a village full of people with Ebola, everyone gets the medicine. It's a real interesting because it's not something that directly affects me. Long term versus short term way to think of things, and actually, it's taken us a little bit longer to deal with Ebola than it maybe should have because we gave everyone the medicine. And I can't say I would do any differently. I probably would give it to everyone too, and just say, look, it's going to take a little longer, but it's going to take a little longer. So anyway, it's an interesting problem though. If you have someone who a disease that really is just deadly, do you really just give something that might cure everyone to half the people? The pictures I have here, Jonas Salk, the man who led the team that cured polio. Polio was a terrible disease that used to just ravage everyone. It was just awful. FDR, one of our presidents, had polio. It was a terrible disease, but has been, largely eradicated by the polio vaccine. It is oddly enough making a comeback along with things like measles, mumps, and rubella because idiots aren't getting their kids vaccinated. Vaccinate your kids. Good grief. Okay. The method science isn't it's the way we go about investigating the world around us, right? It's a way of thinking. Now, it's not the only way of thinking about things, but as I mentioned before when we were talking about the battery, we like it because it gives us answers that we can actually use. Something that is near and dear to our hearts, especially with two tropical storms and a disturbance as I record this out in the Atlantic Ocean, by the way, is, how about average error for hurricane track predictions, right? Where's the storm gonna go? We all want to know, right? Now, right after World War II, there was this effort to stop hurricanes. By golly, we stopped the Nazis, we can stop the hurricanes. And there was even talk about nuking a hurricane. Don't nuke a hurricane. You'll just make a pissed off hurricane. That's not going to work. So once they kind of realized they couldn't stop them, then they started putting their effort into predicting where they're going to go so that you can get people out of the way. Right? That's what we do now. And so, you can see here the... So this is the average error. How far off? Sorry, I'm still drawing. Let me not draw anymore. There we go. So this is the average error. How far off were they? Now you can see here in 1972 they were terrible. I don't know what they did, but they were terrible. Okay, but once again, using the scientific method, right? Use what works, get rid of what doesn't. And with hurricane tracking, that's pretty easy. Where do you think the hurricane's going to go? There. Okay. Did it go there? No. How far off were you? Well, I was, and yeah, right. So you can see though that by using the scientific method, using what works, getting rid of what doesn't, nowadays, well, not nowadays, but through time, you can see how, we're following the 72-hour forecast here. We've gotten better and better and better at it, right? And so now, our 24-hour forecast is, I don't know, what is that, about 100, about 50 nautical miles. Our 72-hour forecast is much more than that, so just a little bit over 100. But anyway, much, much better, right? We got better. We're not getting better because we were sacrificing plumper goats to the hurricane god, right? We're getting better at this because we're using science. Right? It gives you an answer that you can actually use. That's what we like about it. Another thing, and I'm almost done, is the life expectancy. Right? People live longer. Life expectancy in 1900 was about 47 for men and 48 or so for women. Not very much, right? But we're living longer, right? Well, we're living longer because, once again, medical research, right? Stupid things like penicillin, infection. Women, y'all are living longer because you're having babies in hospitals, not in your bedrooms. And so, cesarean sections and, all kinds of things. I mean, childbirth is not uh, you know, the safest thing in the world to do. And so, for a while there, you only lived a little bit longer than we do. Now you live a bit longer because you have fewer congenital diseases, and generally you're not as stupid as we are. But no, but yeah, right. But we're all living longer now. Interestingly, in the United States, this curve has flattened out lately. That kind of has to do more with healthcare than it does. It's like, yeah, we can cure your cancer. You got some insurance, so yeah, that's actually starting to show up in the statistics, believe it or not. So, but anyway, right, we're living longer because of medical researchers like Jonas Salk, and other people who use the scientific method to cure disease and to figure out ways to prevent infection and all kinds of other things. So yeah, so I'm going to leave you with this quote by a philosopher of science named Seth Lloyd. Yes, there are philosophers of science. They don't do science. They just sit around and think about doing science, which is really kind of weird. We don't invite them to the fun parties. But anyway, Seth Lloyd says, okay, look, unlike mathematical theorems, scientific results can't be proved, right? You don't prove anything. They can only be tested again and again and he says only a fool would refuse to believe them. Let's make that a little kinder, until, the weight of evidence becomes overwhelming. Right, once you're talking about conspiracies to hide data or fake data or something like that, no, right, the car battery's dead. Okay, there's the scientific method. Next up will be the beginning of geology, and I believe we're going to be talking about plate tectonics. Okay, I'll get this up, and if you watch this before the weekend, have a good weekend. Okay, bye-bye.